Those are online. Are you able to hear me?
Yes, sir.
No. So listen. Today we are going to start the last chapter of your physics, that is semiconductor physics. So the name of the chapter is Semiconductor Electronics, Materials, Devices, and Simple Circuits. So we'll get started. Listen. So first, we need to understand why we are studying this chapter. Right. So first, let's try to understand the objective of this. Are you able to see the black screen?
Yes, sir.
So notice it. See, this is a very small chapter. Now, first, if you see right, so as the name semiconductor comes into play, right? What do you think we are going to discuss on this? So, if you look at the name of the chapter, what did we see? Semiconductor electronics. It contains the materials and simple circuits related to electronics. So, here when I use the word electronics, what do you understand? Anybody? Can you tell me some electronic goods in this world? So, what are all the electronic goods that we use in our day-to-day life? We can talk about the mobile phone, then laptop, All these things are there, right? These are all the so even in television, right, you have two kinds. One is called as cathode ray tube one. This is not categorized as electronic. So now the ones which we are using are the LEDs. Right? The ones which we are using are the LEDs. What do you mean by LEDs? They are called light emitting diodes. Right? So these are all the electronic components that we can think of. Right? Now the question is, why am I calling it as electronics is because the devices that are used in these particular devices, so the materials which are used in these particular devices are borrowed from semiconductor physics. So we need to understand what exactly a semiconductor means in the first place. So can anyone guess? The name is suggesting semi. It also has a word called as conductor in it. So what is it going to be? So what are semiconductors basically? Can you guess? So name is suggesting you either have materials which are conductors or you have materials which are insulators. If you are able to define a material which is intermediate between a conductor and an insulator, you call it as a semiconductor. So when I talk about a semiconductor, then we can talk about the different kinds of properties it is going to exhibit. So when you talk about a conductor, right? So what comes to your mind? Conductors are those materials which allow charge to pass through them. So when these are the materials which are allowing the charge to pass through them, right? Then what is going to be the resistance of this? Is it going to be high or low? Obviously, the resistance is going to be low. Similarly, when you talk about insulator, these are the materials which are exactly opposite to the term conductor. So the material's resistance is going to be very high in the case of insulators. Whereas when you talk about a semiconductor, it is intermediate to that of conductor and insulator. You will understand, right? So when you talk about the resistance of a material, resistance or resistivity of a material, which falls somewhere between that of a conductor and an insulator, you classify that material as a semiconductor. And the most commonly used semiconductors are germanium and silicon. Clear that? Germanium and silicon. So they are basically the most right. So they are the most commonly used semiconductors. Having this in mind, let us try to understand what are all the topics that are there in this chapter. So basically, the first 7 chapters are the ones which are there. So first one, what we are going to discuss is the first one is we are going to see what is the introduction of semiconductors that I already gave you. Second is we are going to classify the materials as metals, that is conductors, insulators, and semiconductors. And third part that we are going to see is what are the different kinds of semiconductors. One is called as intrinsic and the second is called as extrinsic. And the fourth one is called as a PN junction diode And the fifth part that we are going to see is the semiconductor diode and its application as a device called as a rectifier. So from special purpose PN junction diodes onwards, it is again everything. Okay. So these are the 7 topics we are going to discuss. So as I mentioned already, it has been observed that certain materials like germanium and silicon have resistivity between good conductors like copper and insulators like glass. And these materials are classified as semiconductors. Right. And material obviously which has a resistivity between that of a conductor and an insulator is called as a semiconductor. And the resistivity of a semiconductor is approximately between this value. It is between 10 power minus 2 to 10 power 4 ohm meter, and this happens at room temperature itself. Okay. Now listen. When you talk about the semiconductor, resistivity is inversely proportional to temperature, meaning as the temperature increases, resistivity of a semiconductor decreases. Whereas for a metal, what happens is resistance is directly proportional to temperature. Right? So, as I previously mentioned, previously mentioned, the elements that are classified as semiconductors are silicon, germanium, indium, etc. But germanium and silicon are the most commonly used semiconductors. So, when you want, listen to this very carefully, when you want to describe a semiconductor, right? So, when you want to describe a semiconductor, you can either do it in terms of resistivity or you can do it in terms of a diagram called as energy band diagram, which I'm going to discuss next, and it is very, very important. So I want everybody to pay attention. Are you all listening? Are you all there?
Yes, sir.
Now listen. So I need to discuss about a theory called as energy band diagram. Energy band diagram. Right. So if you see, we have a band. It is not a bond, it is a band. Band means a range. So we have a band called as valence band, conduction band, and something called as forbidden energy gap. Okay. So generally, if you look at a solid, so in a solid, how are atoms placed? So they are placed in a regular repeated geometric pattern, and electrons of the atom are going to revolve around the nucleus in certain permitted energy levels, except this is according to the Bohr's theory, right? But if you look at the electrons, right? But if you look at the electrons which are in the inner shells, so if you look at the electrons that are in the inner shells, they are strongly bound to the nucleus, right? Now, if you take a band which is occupied by the valence electrons or a band having highest energy, we call that as valence band. Meaning, you have valence electrons now. So not all the electrons are going to have exactly the same number of energy. Like it is not going to have exactly the same value of energy. Rather, there will be a certain range of values that are occurring. So if I put all those energy, all those electrons inside a small box like this, where I have varying ranges of energy, then this band is called as valence band. Am I clear with this point? This is a very, very important point. Am I clear with this point? So we saw in the atoms chapter that the energy of the electron in the nth orbital is minus 13.6 into z square divided by n square. I hope you remember this. So when you try to calculate the energy, the valence shell, the energy of electrons and the energy of all the electrons are not going to be the same. Rather, they are going to have a vast range. Right? If you take all those electrons and put it in a box, then that box was given a name called as valence band. And if you look at a valence band may be partially filled or completely filled, but it can never be empty, meaning every particular atom will definitely have a valence shell. So when valence shell is existing, there will at least be one electron in that valence shell that is going to exist. So that is why they told valence band can either be partially filled or completely filled, but it can never be empty at all. Okay. So if you look at some materials, the valence electrons are loosely attached to the nucleus. Right. So when this is going to be the scenario, what can happen? Even at room temperature, some of the valence electrons can leave the valence band. See, guys, tell me only one thing. No? Tell me a logic. If I have a valence electron, for that material to be conductive in nature, how are the valence electrons supposed to be? The valence electrons are supposed to be loosely bound to the nucleus so that they are able to come out of the valence shell and participate in the conduction process. Is that right? So these electrons which are loosely bound to the nucleus are also called as free electrons. This word is again important because we will be discussing a term called as majority charge carriers. So we'll be discussing about majority charge carriers and minority charge carriers. At that point, you should know which particle is what. Okay. And remember, these free electrons are the ones which are responsible for conduction of current in the conductor. Okay. Henceforth, they are also given a name called as conduction electrons. Now the question is, there is an electron. Okay, there is an electron in the valence shell. Right. Once it is removed from the valence shell, what will happen to it? It will start participating in the conduction process. So it will have a higher energy and it will be somewhere over here. Right. So if I'm able to put a box to all the electrons which are participating in the conduction, right? Then I can form a band which is called as conduction band. Is the point here? So what are the two bands that we have discussed? One is valence band and the second is the conduction. Okay. So when you talk about the conduction band, a conduction band can be empty or partially filled. There is nothing like completely filled with respect to conduction band. Okay. So conduction band can either be empty or partially filled. Now, I have a box here where I have all the valence electrons. I have another box which is slightly on top of this box, which I'll call it as conduction band. Right? Now, if the valence electrons are expected to go into the conduction band, I repeat, the valence electrons are expected to go into the conduction band. Yeah. So the electrons, the valence band has to jump to the conduction band. You need to supply some energy to it, right? Are you able to understand? You need to supply some energy so that the one which is at the lower energy can go into the higher energy. So that energy gap that is existing is called as the forbidden energy. Forbidden energy gap. Okay, the separation between the valence band and the conduction band is known as the forbidden energy gap. So if an electron is to be transferred from a valence band to a conduction band, external energy is required, which is equal to the forbidden energy gap, and that energy gap is generally measured in terms of electron volt.
Sir,
Tell me.
you're telling it as the separation, but you are measuring it in EV, sir. Right?
Energy, forbidden energy gap, energy means how much energy I'm supposed to supply for the electron to jump from the valence band to the conduction band is measured in terms of EV, EV in electron volt.
Okay, sir.
Electron volt is the unit of energy then.
Yes, sir.
That is what I told. So forbidden energy gap is measured in terms of electron volt. Nitish, understood?
Yes, sir.
Hmm. Yeah, right. Part and all it's theory type. We know it is right. So the energy band diagram will look something like this. Energy band diagram will look like this. You have a valence band, you have a conduction band. So the amount of energy that you need to supply for the valence electrons to jump to the conduction band is called as forbidden energy gap, and it is measured in terms of electron volt. Okay. So if you obviously try to explain the materials of insulators, conductors, and semiconductors with the help of an energy band diagram, what would you say? If I give you an insulator, what do you think will be the energy band gap that is existing between the valence band and the conduction band? Will it be more or less? Will it be more or less?
More, sir.
It should be more, right? So in general, the forbidden energy gap is more than 3 electron volt, and what will happen is almost no electrons are going to be available for the conduction process. So if you see the energy gap that is existing between these two, it is going to be somewhere around 3 electron volt, meaning there is almost no electrons that are available for conduction. That is why insulators are bad conductors, right? So if you observe materials like glass, the valence band is completely filled at 0 Kelvin itself. Okay. So the energy band, the energy gap between the valence band and the conduction band is of the order of 10 electron volt. Right, for a glass, if you take it is going to be somewhere around 10 electron volt. So we know that there are different processes in which we can generate the free electrons. This we discussed in the dual nature of matter chapter. Right, there were different kinds of emission. One is thermionic emission, then you have field emission, then we have photoelectric emission, right? So what will happen is, if you take an insulator, if I take an insulator and if I place that insulator even in the presence of very high electric field, you cannot generate electrons. Okay, right? Similarly, when the temperature is increased, there will be some electrons which will move to the conduction factor, but that is also very less. So this is the reason why when you try to explain the same insulator in terms of energy band diagram, we are able to understand that the energy we need to supply for the electrons to go from valence band to the conduction band is very high. That is why these materials are not good conductors. So that is why the resistivity lies somewhere between 10 power 11 and 10 power 16 ohm. We have semiconductors. So when you talk about the semiconductor, the forbidden energy gap is very small, right? So if you take germanium and silicon, these are the best examples of semiconductors. So if you observe, there are no electrons. So generally the forbidden energy gap is of the order of 0.7 electron volt for germanium and 1.1 electron volt for silicon. Okay, but if you see, there will be no electrons in the conduction band, but the valence band will be completely filled at 0 Kelvin. So even with a small amount of energy, the electrons can easily jump from the valence band to the conduction band. Okay. So what will happen here is, when you raise the temperature, the forbidden energy gap is decreased and some electrons are liberated into the conduction band. And if you look at the conductivity of a semiconductor, it is somewhere around 10 power 2 Ohm inverse, meter inverse. So I hope this clear till this step. Right? Similarly, when you talk about a conductor, there is almost no forbidden energy gap. Means the valence band and the conduction band almost overlap each other. Okay. So what will happen is, due to this overlapping, even a small potential difference, right? Even a very low potential difference can cause the continuous flow of current because it is easy to send an electron from the valence band to the conduction. So it is going to look something like this. Third one is for insulator, second one is for semiconductor, and the first one is for the conductor. Okay. Is it clear, guys? Is there any doubt? Next is the concept of electrons and holes in semiconductors. So if you take the electrons in an intrinsic semiconductor, right? If you take an electrons in intrinsic semiconductor, I need to explain what this intrinsic and extrinsic is. Listen to this. So listen to this concept. So when I talk about a semiconductor, then it is basically classified into two types. One is called as intrinsic, and the second is called as extrinsic. So intrinsic semiconductors are pure form of semiconductors. Okay. Whereas when you talk about extrinsic semiconductors, extrinsic are impure form. And when you look at intrinsic semiconductors, they are not good conductors of electricity. So, to make an intrinsic semiconductor into a better conducting material, right? In the way we make it as we make an intrinsic into an extrinsic through a process called as doping, which is doping. Through a process called as doping. So here what we do is we do impurities. So we do impurities in such a way that these impurities will make the material a better conductor. So these impurities will make the intrinsic semiconductor a better conductor. That is, for intrinsic to be converted to extrinsic, we need to carry out a process called as doping. So doping means adding impurities. So this is a very, very, very important point to be known. So am I clear with this point?
Sir,
Listen to this carefully.
sir,
Ah,
sir, these impurities must liberate electrons, sir.
impurities means
These impurities should be able to liberate electrons.
not only electrons, they can release another particle also called as hole. That is what we are going to discuss next.
Okay.
So now what we are going to do is we are going to see a topic called as electrons and holes in semiconductor. See, you have electrons in an intrinsic semiconductor, means they are pure form of semiconductor, right? So if I take an intrinsic semiconductor and I subject it to a very high temperature, then what will happen is electrons will start moving in the conduction band, and those electrons are called as intrinsic carriers, right? So when the electron, listen, when I have an electron in the valence band and I have a conduction band here, when an electron jumps from a valence band to a conduction band, what is created here? There is a vacancy, or can I say there is a void? Can I say that there is a void present? Right. So what will this void have? This void will have the tendency to receive the electron back. Means if you take an electron closer to this void, the electron will tend to get attracted to it. So it is acting like a positive charge, but it is not an actual positive charge. It is a virtual positive charge, can I say? It is a virtual positive charge, and that virtual positive charge is occurring due to the vacancy that is created, and that vacancy is given a name called as hole. Okay. So if you consider the case of, listen, when I say pure germanium crystal, I'm talking about intrinsic. So when you consider the case of a pure germanium crystal, it has 4 electrons in the outer or valence orbit. Right, germanium and silicon, if you see, they have 4 electrons in the outer orbit. So when you have 4 electrons, what kind of a bonding does it participate with the neighboring particles? It is called covalent bonding. Right. So these electrons, when 2 atoms of germanium are brought close to each other, you will have a covalent bond that is formed between them. Correct? Right. A covalent bond is formed between them. If some additional energy is received, so what will happen is when the covalent bond is formed, if we supply some additional energy, then there is a possibility that the electrons, one of the electrons that is participating in the covalent bond will break and it will become free to move within the crystal lattice. Am I right? So there is a possibility that the bond will break and the electron will become free and start moving within the crystal itself. As a result of which, there is going to be a vacancy created, right? There is going to be a vacancy created. Am I right? Now, so when that electron has come out, see, observe at this point. You're able to see one electron has come out. Yeah, one electron has come out. So what is that you're able to see? You're able to see circle which is open. So there are two kinds of circle drawn. One is a closed circle. So closed one is the electron. So the open one is the vacancy, and that open one is what is called as hole. Seriya? Puriyudha? So that's called as hole. Now, what will happen when this hole is created? What will a hole try to do? I told you hole is a virtual another. Hole is virtual positive charge. So yeah, electron negative. So hole is going to be a virtual positive charge. So positive charge, what will you try to do to the neighboring electron? It will try to attract. So when this hole is formed, look at the diagram, okay? When this hole is formed, what will happen is this electron has escaped, okay? But an electron from the neighboring atom will try to come and cover this hole. When this neighboring electron comes and covers the hole, what will happen here? There is a hole created. This electron will come and cover this hole. Again, a hole is created here. So what has happened is, initially the hole got created on the left germanium atom. Right? Then the hole started traveling like this. So this is first, second, and third. Right? So the hole started traveling. Right? When this is going to be the scenario, right? Can I say that the whole current is formed? Can I say that the whole current is formed? So what do I mean by whole current here? So something is moving, it's called as current. So what is moving here at first? Another is the whole current. But actually, who is moving to create this whole? The electrons. So electrons, when it is trying to cover, when it's trying to cover the hole which is getting created, we are able to see that the electrons missing at a particular place is creating a vacancy, due to which it is appearing as if the hole is traveling from one point to another. So that's why we call this as a hole current. Okay. Guys, are you able to understand? Okay. So one point that we can clearly notice, if electron moves from negative to positive terminal, or hole starts moving exactly the opposite direction. So, clear? So this is what we call it as hole current. Okay. So I have already explained what is an intrinsic semiconductor. A semiconductor which is pure and contains no impurities called as intrinsic. So in an intrinsic semiconductor, the number of free electrons in the holes are equal. So number of electrons will be equal to the number of holes. So common examples of intrinsic semiconductors are again germanium and silicon. Right. So this we have already discussed that when you take a semiconductor, the forbidden energy gap is so small that even at room temperature, there are many electrons which possess sufficient energy to cross the forbidden energy gap and they enter into the conduction band. Right? So this is what happens. But the ultimate thing is, the point that you need to make a note is, intrinsic semiconductors are bad. We have already written. Intrinsic semiconductors are So, intrinsic semiconductors are not good conductors of electricity. Hence, in order to make it a better conducting material, we do follow a process called as doping. Okay. So, how they can? So, by doping, what you're going to do is you're either going to generate excess number of electrons or excess number of holes. Because in intrinsic semiconductor, what is the relation between number of holes and number of electrons? We just saw. Oh, here is number.
Holes electrons equal.
They are equal. No, number of electrons is equal to number of holes in the intrinsic semiconductor. But when you dope something, right, there is a possibility where you can increase the number of electrons or decrease the number of electrons. Right. So if the number of electrons is greater than the number of holes, it is called as an N-type semiconductor. Whereas if the number of holes is greater than the number of electrons, it is called as P-type semiconductor, which is going to be the next topic of our discussion. Okay. So here you need to make a note that the impurity that you're trying to add, you will not add too much and all. You will only add 100 parts per million. Okay, 100 out of 10 power 6. And this process of addition is a process of addition of a very small amount of this impurity to an intrinsic semiconductor is called it's called as the doping, and the impurity atoms that you're adding are called as dopants. Okay, and the semiconductor that contains the impurity atoms is known as impure or doped or extrinsic semiconductor. Here, okay. See, there are different methods of doping and all, which is actually not important for you. Right. So one last point I would like to mention here is when you're talking about the impurity, that is the doping material, it can either be pentavalent atoms like bismuth, antimony, phosphorus, and arsenic, which have 5 valence electrons, or trivalent atoms, which are aluminum, gallium, indium, boron, which have 3 electrons. Sorry, 3 valence electrons. So the pentavalent doping atom is known as donor atom because it will give excess electrons, and the trivalent is called as acceptor atom because it gives a hole. all from my side for today. Sure. So by next class we'll be done with this chapter. So if there are no doubts, we can wind up. We'll wind up.